Hi, this is Leach with Simpson Math, and in this video, I'm going to introduce you to the shell method. The shell method is another method to find the volume of a plane figure that's been revolved around a line. So let's get started. So I have this applet I'm going to use to introduce this to you. So I have this basically looks like a parabola that's been turned upside down. Let's find where's this volume going to be? So I'm going to, it says slide me, so I'm going to slide it. Alright, so this is our figure here. Kind of looks like a cone that's been smushed in a little bit. Alright, so if I was to need to find the volume of that, now we could do the disc and washer method. The revolving around or finding the cross-section method, that's not how this was created, so that wouldn't work. But we could do the disc and washer method. But for this particular case, it might not be as straightforward. Look at what we'd have to do. I'd have the disk method for this first bit, and then we'd have to switch over to the washer method. So not impossible, but doable. So this is just another tool in your tool belt that in some cases, like in my opinion, for like this one, would be quicker to actually set up and get going and get working. And we often tend to avoid squares. Like you know how the disk washer method had all those squares. Whenever you would square the radius, we kind of get to avoid that. So what's different about the shell method? Well, let me grab this dot, move it over a little bit. So I had this rectangle, and notice it just created this cylinder here. And so we're going to be using a whole bunch of cylinders to create this, hence the shells. These cylinders are these shells. Okay, so let me flip this back and transport you back to the beginning of this semester when you learned about integration, and you first learned about integration using all these rectangles, right? And with these rectangles, these were just approximations. Sometimes you use rectangles, sometimes you use trapezoids, different sort of shapes to approximate the area under the curve. But they reached a point that you're like, you know what we can do with these rectangles? We can just make them smaller, right? Smaller and smaller and smaller, 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 until basically they're so small, they're infinitesimally small, they have no thickness at all, and I can just add all those up, basically really add up all those heights. So we're going to be doing that same thing here, but instead of having with all these rectangles, but then we'll just revolve this around, and notice how it pops, and we get that cylinder here. And then what we'll do is then we'll take not just this one cylinder, but we'll have many cylinders. So cylinders going all the way from A all the way over here to B. If I add up all of those surface areas collectively, I will then get a volume. So add a plus, 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 add them all up. Then we get the that surface area. Oh, sorry. Then we'll get that volume by adding all of those up. All right. Let me take this back just a sec so the solid cylinder goes away. There we go. All right. Let's break down where that cylinder is and the components of that cylinder. All right, so cylinders have a radius and a height. So if I know the radius and the height, I could find the volume, the surface area, lateral surface area of that cylinder. So what is the radius of this cylinder? Well, as you can see, it is this distance from here to there. Oops, I clicked and added a dot. That was unusual. Oh, just darkened that one. All right, so then it's this distance from here to there is a radius. Well, what is that distance? That distance is just x. So in this case, when you're revolving around the y-axis, your radius is going to be x. Now, if for some reason it's revolving around like a vertical line that's maybe been shifted over some, then your radius might be something plus or minus x. But when it's just the y-axis, it's just x here. All right, now what about the height of this cylinder? All right, let me make this a little bit more solid now. So what about the height? Well, the height of that is just f of x. That's just a function, f of x. So if I know those two values, I can determine the volume and the surface area of these cylinders. So here's this note that I've made. So my radius is that x-axis, the x value is the radius. The height is the f of x. So just a little geometry reminder that the lateral surface area, so you see the above picture that is more solid, the area of our shells, the lateral surface area of a cylinder, it's 2 pi r times h. Now what is that? Well, that's the base times the height. So here's a can of honey roasted peanuts that we were snacking on the other day. I mean, just a few minutes ago, actually. So if I was to take this paper, this seam is around here somewhere. If I was to take this paper and tear it open, it actually would be surprisingly long. That length is actually the circumference of the base of this can. And then the height would then just be this height. So the lateral surface area is the circumference, or 2 pi r, times height. There's this lateral surface area because if I was needing to manufacture this and get this label printed, I would need to know the area of this, so that way they would charge me for every single one of those labels I get printed. So we need to know that area, not the tops or the bottoms. That's not getting printed. So 2 pi r times h. So the area of our shells, the lateral surface area of a cylinder. So in terms of this diagram, instead of 2 pi r, it's 2 pi x. Instead of height, it's just going to be f of x. All right. So in this case, the f of x would be like an upside down parabola, which would still be in terms of x. Okay, so if we have an infinite, we have an infinite number of these cylinders or these shells, so we can integrate with respect to x from point A to point B, sum all those up, and that gets our volume. So I'm going to show you one more kind of applet simulation thing, and it will help us get a better picture of a real problem that we're going to be doing today, because we know what the function is. So here we have the function x minus 1 times x minus 3 squared, and that's going to be our first example that we're going to do. Okay, so before we dive in, let's figure out what's going on with this function. So it's this cubic. It is x minus 1 for its root, and then a double root at x minus 3. So that means that it is, I can flatten this up so it's, that z-axis is just going straight to your eye. So we have from a to b, where a is 1, because that's that root, and a double root at x minus 3, or sorry, double root at x equals 3. So this actually is going up, going to touch and turn at 3 and move on up. That's why we're bounding from a to b here from 1 to 3. So just this little section right here. Okay, so how do I get the volume? Where's this revolution? So here I'm going to be revolving around the y-axis. All right, now before I just pop that out, let me show you what these shells are going to look like. So here's a cylindrical shell, that height that you saw there. So that colored in height right here, that is the height of that cylinder. The radius is just simply x. Right? So I can move that up here, and you can see this radius is x, and this height is the height of the function. Okay, so let's trace this cylinder. So let's have this move around. It's less finite as the other one was, but you can see we move this around, so you can see this in 3D space a little bit. How it gets thinner as it moves on, and has this empty section in the middle. You push this button so you can see. Looks kind of like a Jello mold. So there we go. So there's this 3D figure, this object that we're trying to find the volume of. Okay, so, well, let's do this. Alright, so we're going to compute the volume of a plane figure bounded by, so there's that function we just saw. It did switch the two factors, but same difference. So x minus 3 squared, and then x minus 1. So there's our function. Alright, so bounded by this function, and then the x-axis on the interval from 1 to 3. Right, and then we're rotating it about the y-axis. Okay, so here's our region that we're looking for. We just saw that over there, revolving around the y-axis. There's a bit of that kind of our circumferences that we're looking for. There's that height, and there's that kind of other cross section that we would see. All right. So if you look above my head, right here, that if we're revolving around the y-axis, it's just going to be the volume is 2 pi times the integral from a to b with the radius, and our radius is x, and our height is then this f of x, which in this case is x minus 3 squared, and the x minus 1. Notice if you were to have to do disk and washer method, you would have to split. You'd have to do washer method and split this here. Have to mess with radius squared, so that could be an issue with some things. But this is just another tool in your tool belt. All right, so let's look at this. So if I have the volume of, and here's that same thing set up. So 2 pi times the integral from 1 to 3 of x. So notice 2 pi x, that is the circumference of that big circle, the circumference of the base of the cylinder, base of each and every cylinder, times the height of those cylinders. And notice that this is with respect to x, because as x changes, all this will change. So then our function times dx. All right, so now we're just going to integrate this, and this integration is pretty straightforward. If you go back in time just a few weeks, your few weeks ago self might be like, but your current self should be like, piece of cake, right? Because notice we just have to distribute, FOIL this out, so write it twice in FOIL, and we end up with this cubic. Then I went ahead and did x times x minus 1, so I get this binomial. I just put it first so that we do binomial into the cubic. This is, binomial into this quadratic here. Might be a little bit easier, this 3-term polynomial. Distribute that out, and we end up with this 4-term polynomial, this quartic. And then integrate. So if I do this, let's just look at this one. So if I was to integrate just this one right here, negative 7x cubed, well then that's just using the power rule. So it would be negative 7 plus 1, so it's negative 7 fourths times x to the 4th. And all these just use that power rule, so it's pretty straightforward. And then evaluate them from 1 to 3. So there's all of our 3's minus the 1's. Don't forget to distribute. I'm sure we've all made that mistake a time or two. I know I have. So make sure to distribute the negative to all the parts. And then combine like terms, and we get a pretty decent, just a little 12 fifths. 2 pi times 12 fifths is 24 pi fifths. All right. So the volume of this that we were just looking at, the volume of this is 24 pi fifths. All right. How about that? Okay. So now let's do one more problem. We're going to compute the volume of the plane figure bounded by f of x is the cube root of x, and the x-axis from the interval of 0 to 8. All right, and then we're rotating it about, this time, the x-axis. All right, so don't freak out. It's all good. You've done this before, but do be careful when this is the x-axis. So since this is around the x-axis, point this way. I'm going to show you right here. So everything here is going to be in terms of y. So we need to be aware of that since we're rotating around the x. This is a little bit different than some of the other washer cross sections. Like your point of view might be a little bit different in terms of x's and y's. But here, this is in terms of y's. Right. So here is our cubic, that section from 0 to 8, just that part from 0 to 8, that cube root rather. All right. And then I want to go only from 0 to 8 and find the this shaded region. This is our plane figure here, and then I'm revolving it around the x-axis, and that will get us that figure that we're looking for here. Okay, so let's find the cylinders that are here. Since I'm revolving it this way, I have circles going this way. I'm just going to turn this for just a second, because you might be able to see the cylinder a little bit easier here. So there's the base of my circle, really, really tall, skinny cylinder rotating right here. Right? So then my radius is this right here, and put this back to viewing it normal. We see that our radius is y. So since our radius is y, so then our radius is y, period. Okay, so now I need to find the height. So my function is in terms of x. Since I'm switching and looking at it differently, I need to find this in terms of y. So f of x is the cube root of x. So I can cube both. So f of x is really just y. I can cube both sides, and I end up with y cubed equaling x. Right? Now, is that y cubed just our height? Is it just automatically whatever that function value is? Well, not so much. So in this case, if this was y cubed only goes to here. Y cubed doesn't take me this part. So if I used y cubed and integrated from 0 to 2, I would get this shaded region, and would find the area, the volume rather, from all this revolved around would be like a weird, like very pointy, like shot glass type of thing, really tall, skinny, like shot glass looking thing. So nope, we need to make sure we have to flip this around. So this is 8. So if I do 8 minus this segment right here, this y cubed, I'll get this distance right here. And that works for all values of y. Up here at 2, it would actually just be 0. If if I down here, it would be all the way at 8. Whereas here at 1.5, I would get this section here, and then subtract that from 8, and I would get that portion there. So that would give me that right height. All right. So now I know my height is 8 minus y cubed. My radius is just simply y. Again, if I had this and I was revolving instead of around the x-axis, but bump that up twice, maybe revolving around y equals 2, I would then have to maybe add or subtract 2 or something to the y in order to have it be in the right spot. But this is just on the x-axis. And then, again, I could use disk and washer, and probably, admittedly, disk would be easier on here than what we're doing here. But we do have a benefit of not having to square our radius. Our radius is just going to be there by itself. So that does add maybe a little bit level of ease. Right, so let's put this together. So we have the volume is this 2 pi times y. Again, 2 pi y, that is the circumference of the base of each and every one of our shells or our cylinders. And we are integrating from the with respect to y. A second ago I did this and did it from with respect to x, 0 to 8. I got a negative volume. That's a big old indication that you did something wrong if you get a negative volume. So 0 to 2, make sure it's in terms of y. Yeesh, that was a scary moment. It was like, oh gosh, everything I knew is wrong. Nah, just mistakes happen. So I then get y times 8 minus y cubed. This 8 minus y cubed is the height. If you want to think of it as a length, because it's over on its side, it's not a height this way, it's a height this way. If you want to call it length, whatever, don't care. Height, length, whatever. And then again, it's in terms of y, so everything is in terms of y. Don't have to mess with that. So then we just integrate it. I multiplied the y. This is again the power rule, so that's pretty straightforward. Evaluate from 0 to 2's. These zeros go away once you evaluate them, so it's really just the 2's. And we do end up with a positive number here, so when you multiply it out, you get 96 pi fifths. So that's good to go. So that's the volume of this figure right here would be this plane figure rotated around the x-axis. That is has a volume of 96 pi fifths. Leave it in terms of pi so we can keep it nice and accurate. Well, there you have it. I hope these 2 examples and my introduction helped you understand this shell method. Just another tool in your tool set to help you figure out the volumes of these plane figures that get revolved around all these lines. Lots of fun. Love this part about calculus too. So hope this helps, and we'll see you in the next one.